Welcome to binomial distribution. Binomial distribution is the next step beyond discrete probability, and what I would actually say is that binomial distribution is a subset of discrete probability. And we're going to go through this example to kind of illustrate what binomial distribution actually is and what it's useful for. So we've got a very basic example, flipping a coin. We've got heads and tails as our two possible outcomes, and we know that these are equal probability. So the probability of flipping a head is 1/2. The probability of flipping a tail is also 1/2. Now, what if we have the situation where we flip the coin, let's say 4 times, okay? So we flip the coin 4 times. What's the probability that out of those 4 flips, only one of them is going to be a head? Now, a lot of people would try and jump to get the answer straight away. And what they'll say is, okay, we have one head out of 4 flips. So what we do is the probability of flipping just one head is 1/2. And then the probability of flipping 3 tails, because obviously that's the remainder, is just going to be 1/2 multiplied by 1/2 multiplied by 1/2. All grouped together, you can kind of think of it as. So that's 3 different tails probability. And obviously you can see they're all the same anyway, because the probability of tail is equal to the probability of heads. So a lot of people would say, okay, it's just 1 over 2 to the power 4, which is 1 over 16. But I'm just going to give that away. Before you jump off the video, that's actually incorrect. That is actually not the right way of answering this question. And that's for one kind of, not simple reason, but one reason that a lot of people overlook. It's the fact that when you have this type of wording where you want one head out of 4 flips, it doesn't matter what the order is. So when we did that calculation before, you saw that I put the head probability first and the tails probability after that. So that assumed that the order was going to be head, tails, tails, tails. But if you look at this order now and you kind of reread the question, you could kind of see that the order doesn't actually matter. So you could have tails, head, tails, tails. You can have tails, tails, head, tails. You could also have tails, 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 heads. So you can see we actually have 4 different combinations of the same probability. And you can see the probabilities actually wouldn't change either way because flipping coins are independent events. So it doesn't matter. The calculation we did before is correct for all orders, right? It doesn't matter where the 1/2 goes because, yeah, we have independent events. So what we can do is actually just multiply the probability that we had before by 1 over 16. As not 1 over 16 was the probability, multiplied by 4 because that's how many combinations we have. So we have 4 different combinations, so the probability that we had before was 1 over 16. So our final probability is actually 1/4, much greater than 1 over 16. And that's purely because we have a lot more combinations that we have to take into account. Now in this case, it's pretty simple. It's a pretty simple way of figuring out how many combinations there are because you only have one success. So we call a head a success because that's what we're focused on in this event. We only have one success out of 4 trials, so it's really easy just to list out all the different combinations. But what if you have a more complicated task? Let's say if we had 12 coin flips and you wanted to see what's the probability of flipping, let's say 3 heads out of those 12 flips. It would be a lot harder to figure out from scratch, like we did here, how many different combinations there are. So in the next part, we're going to kind of develop a formula and then show you how to apply it as well.